In this video, we're going to focus in on the gases and their properties. Just to summarize what we know about gases, in terms of the gases, they expand and they fill a container, so they take the shape of the container and the volume of the container. So they're very expandable and compressible. It turns out then that they readily form mixtures with other gases because there ultimately is lots of empty space, and the overall interactions between the gas molecules is a result of them bouncing around within the container. To summarize these properties, we have developed the so-called kinetic molecular theory of gases. Turns out that the idea that the gases behave like a so-called ideal gas is a major assumption, and so we need to understand some of these properties of an ideal gas. First of all, the volume of an individual molecule is negligible or very, very small in comparison to the size of the container. So there's lots of empty space within the container. Gases are comprised of very small individual groups of atoms or individual atoms that are in constant motion, and when these molecules collide with one another, the collisions are completely elastic as a result of the fact that intermolecular forces between these molecules is essentially non-existent. And then in addition to that, the energy or the kinetic energy of a particular molecule can be transferred from one molecule to another as a result of these collisions, and as a result they behave much like billiard balls that are colliding with one another on a pool table. And as a result, then also the average kinetic energy of the molecules is what we know of as the temperature. One of the properties of a gas is the fact that it exerts a pressure. We can define pressure as the force per unit area, and the equation for pressure is given here. So P is typically the symbol we use for pressure. F is the symbol we use for force, and area is A. And area is going to have units of either meter squared or some distance times another distance. And so there are other than derived units for the pressure that, as you see here. First of all, we have the Pascal, which is equivalent to a Newton per meter squared. We also have millimeters of mercury, which is the height of mercury in a typical barometer, and so these are the an often used pressure unit. We also have atmospheres, and then we also have the so-called torr. The relationships are such that 1 atmosphere of pressure, the amount of force per unit area that the Earth's atmosphere exerts on a surface at sea level on an average day, is equal to a barometer that is 760 millimeters high in terms of the height of a mercury barometer. It turns out that also the millimeter of mercury is given the symbol of torr, which is named after an Italian scientist. His name is Torricelli, and so 1 millimeter of mercury is also a torr. And then we have the relationship that 1 atmosphere is also 1.01 times 10 to the 5th pascals. Or if we can convert those into kilopascals, 1 atmosphere is 101.3 kilopascals. Shown here is a typical mercury barometer. The reason that we often use mercury in a barometer is that it has a very high density compared to most liquids, and therefore the barometer doesn't need to be extremely tall to measure pressure effectively. So to make a mercury barometer, essentially we have a glass tube that has been sealed at one end and then filled completely with mercury and inverted and placed down into an open container having liquid mercury in it. The mercury having weight then will then be pulled down towards the surface of the earth, and it creates a small vacuum up at the top of the tube that has a very small amount of mercury that evaporates into the gas phase. Counteracting this force of gravity acting on the mercury is the fact that on the outside of the barometer, on the surface of the pool of mercury, is the atmosphere pushing down on that surface, and when those two forces come in equilibrium with one another, we result in then a mercury that is in the tube, and on an average day at sea level, the height of that mercury will be 760 millimeters. This is essentially known as also 1 atmosphere. If the pressure on the outside atmosphere decreases, as on a day when it might be a storm coming, then that outside pressure decreases, and as a result then the height of the mercury will go down. And then on a nice day, if the atmospheric pressure is high, then the height of the mercury column will rise, and we say that we have a higher pressure than 1 atmosphere. If we were to take a container and remove all of the gas molecules, we would have what we call a vacuum. This is a situation where no longer are these gas molecules available to collide with the inside surface of the container, and that can be a fairly big problem if you have a situation where there's a lot of pressure on the outside of a container but very little on the inside. Turns out that at sea level, using English units, 1 atmosphere of pressure is equivalent to 15 psi, where a psi is 15 pounds per square inch. And this can be a significant amount of force, and so as you see here in this picture, this is a tanker car that was evacuated to form a vacuum on the inside of the container, and the tanker car completely collapsed as a result of that. Shown here is a device that could be used to measure the pressure inside a container, and what you see here is a glass U-tube that has been filled with mercury, and if we have a glass bulb that is connected to the U-tube with a valve up there at the top, we see that the height of the mercury on the left side of the U-tube is higher than the height of the mercury on the right-hand side, and this means that the pressure inside of the glass bulb must be lower than the atmospheric pressure of air pushing down on the right-hand side. And so the difference in the heights of the two must represent the pressure difference between the two gases. And in this case, the pressure inside of the glass bulb is less than 1 atmosphere of pressure. Conversely, if the pressure inside of the glass bulb were higher than the atmospheric pressure, then the level of the mercury on the left side of the tube would be lower than on the right-hand side, and this would be a situation where the difference in the heights would be the pressure inside the tube plus whatever the difference in the height of the mercury in terms of millimeters of mercury. So at this point, we can define what an ideal gas is and compare these properties to what real gases behave like. So an ideal gas is a substance that has no molecular volume. So as a result, you can apply pressure to it, and the pressure would never cause the molecules to actually come in contact with one another. And then likewise, the collisions for an ideal gas are always elastic, so we always have these molecules bouncing off one another, and therefore they never become liquids or solids for that matter at very high pressures and low temperatures. This is not what actually happens for real gases. And of course, for a real gas, there is a molecular volume. So at some point with very high pressures, and if the container is causes the volume to be of the container to become very small, at some point the molecules come in contact with one another and are forced to interact to some extent. And of course, in real gases, there actually are significant intermolecular forces which cause the molecules to stick to one another to some extent. The real gases that most behave like ideal gases are very, very small gases like hydrogen or helium. And so, in fact, elemental helium does not actually become a liquid until a very low temperature at extremely high pressures, and its boiling point actually is about 4 degrees Kelvin.